Hello, how are you doing? This is Mike again, and we're going to calculate another volume. And in this question is going to be slightly different than ones we completed prior to, because this one we're going to rotate about a different axis. And in the prior questions, we've looked at the x-axis and the y-axis being the axis of rotation. But in this example, we're going to actually revolve this about the line y equals to 4, which is a horizontal line. So again, working through our same protocols, our first step in this is to actually go ahead and graph this guy. So I'm not going to go ahead and get too in depth with the graphing of this function, but it's going to look something like this. So we know what our normal cubic function looks like. The fact that we're dividing it by 2 gives us a little bit of a skinnier function. It sort of squeezes it in a little bit closer, centered to the y-axis. So it looks something like that. I'm going to go ahead and then evaluate and recognize that we're looking at the line y equals to 0. Y equals to 0 is going to be the horizontal x-axis. So we got the line y equals to 0 here. And then we have the line x equals to 2. So we have the line x equals to 2, which I'll do in blue. And that's going to be this guy right here. Doesn't matter where I draw it. And that's going to be the line x equals to 2. And now we have to see exactly the line y equals to 4. It did work out very nicely here because our axis of rotation does intersect right here. So if we look at y is equal to x cubed over 2, when x is 2, we get 2 cubed all over 2, which gives us a value of 4. So we're going to rotate it at the intersection, which is here. So it's going to be our line y equals to 4, and we're going to rotate it right around that axis. So, whoops, that's a little bit not very straight. Still not straight. A little bit better. A little bit better. So what do we have? We have this solid that's created right in here. So we have this solid that's created right in here. I'm going to indicate some critical points. So I have 0, 0, and then I realize here that I'm going to have the point 2, 4. So I have some critical points. This point is 2, 0. I don't know if that's really going to be helping me, but we never know. So I'm just going to start labeling some points, and then I'm going to rotate it about this axis. So I'm going to go ahead and redraw this, accentuating those more critical areas, So let's go ahead and redraw. Let's go ahead and redraw this. So we're going to have something that looks like this. Okay, so we got this coming down, and we got this axis of rotation, which is this guy right here. And that's going to give us something that looks like this. Okay, so we have something that looks like this. So now instead of rotating about the x-axis or the y-axis, we are going to look at this axis of y equals to 4. So hopefully we're all seeing here that there's two different mechanisms we can go about solving this. We can use the shell method, or we can go ahead and use the washer method. For this one, I'm going to use a washer method. I like using washer method in this example. It just tends to work very well. So the first thing I'm going to do is I'm going to draw my washer. So remember, a washer has an inner radius and it has an outer radius. So a washer has an inner radius and then it has an outer radius. So it has it's missing a volume in the middle. I call this the lumen of the solid. So first of all, I'm going to go ahead and draw my inner washer. I'm going to draw my inner washer. So this is the inner portion to my washer right here. And I'm going to go ahead now, and I'm just going to switch this, and I'm going to go in green, and I'm going to look at the outer portion of my washer in green. So hopefully we all recognize that with the washer method, I'm looking at the axis of rotation first. The axis of rotation is a horizontal axis. So it's a horizontal axis. It does fall in the form of y equals to 4, but it's horizontal just like the x-axis. So I think that if it's a horizontal axis, I want to integrate with respect to x. So since I have a horizontal axis I want to integrate with respect to x, my radii must be perpendicular to the to the line y equals to 4. So let's go ahead and I'm going to tackle the outer radius first. So I'm going to look at the outer radius first. So let's look at the outer radius. So from here to here, from top to bottom, my outer radius here is, how do I find this outer radius? What is this outer radius from here to here? Same thing that the outer radius is from here to here. The outer radius from there to there is the same as it is from there to there. If I were to look here, the outer radius here is going to be the same as the outer radius in our first washer that's created. The outer radius is constant. The outer radius is constant because it's constantly going to the x-axis here, or it's constantly touching the line y equals to 8. That outer radius is not changing. So notice we have the outer radius from here to here. It's a value of 4. The outer radius from here to here is a value of 4. The outer radius from here to here is also a value of 4. So the outer radius is constant at a value of 4. Now we have to tackle the inner radius. So I'm going to go ahead and I'm just going to erase my outer radii just to make it a little bit easier to visualize, because I think some of these colors might cause a little bit of an issue. So let's go ahead and look at the inner radius. So the inner radius. So I hope we all recognize that from here to here, this is a value of 4. From here to here, this right here is a value of the curve. This right here is that curve of y cubed over 2. So this right here is the curve x cubed over 2. From here to here, this is the curve x cubed all over 2. From here to here, this is the curve x cubed all over 2. But we're looking for the inner radius, which is in actuality from the line y equals to 4 to the curve going down. So we are looking in actuality for that guy right there that I highlighted in green. So if we see the larger distance is 4, and the smaller distance, and maybe we can show in blue right here. If I want to find the radii that's in blue, I know that I'm going to take the larger, subtract off the smaller portion, so the inner radius is going to be a value of 4 minus x cubed all over 2. 4 minus x cubed all over 2. So now I know my outer, now I know my inner. I can go ahead and perform and execute the integration. So since I'm integrating with respect to x, I'm going to look at my x boundary, which is going to start here at 0, and then it's going to go all the way to 2. Start here at 0, go all the way to 2, because this is 0, 0, and this is going to be 2, 0. I'm not integrating with respect to y. However, I could have performed this problem. And integrated with respect to y. So I would not have used the disk method. I would have used the shell method. So, but for me, I'm going to go ahead and use the washer method. So the washer method states that we are going to integrate from 0 to 2, of the relationship of pi times the outer radius squared minus the inner radius squared, and this will be with respect to x. This will be pi integral from 0 to 2 of the outer radius, which is going to be 4 squared, the outer radius, which is 4 squared, minus the inner radius, which is 4 minus x cubed all over 2 squared, and this is all with respect to x. Continuing, I'm going to keep that value of pi out in front. Integral from 0 to 2 of 16. I'm going to keep this subtraction sign there. So that's going to be 4 squared 16 minus 8x cubed minus 8x cubed. So this will give us minus 4x cubed plus x to the 6 all over 4 dx. Yeah, so it's 16. Oh, and then I have to minus 16. I forgot to subtract 16. So all I did was just FOIL out. Positive 16. That's right. So 4 squared is positive 16, and this is all with respect to x. So this will give me pi. I lost this portion up here. Don't know why it just decides to delete things. So we're going to integrate from 0 to 2. So we're going to have 16 minus 16 gives us 0. So this will give us 4x cubed minus the value of x to the 6th all over 4 with respect to x, keeping the pi out in front. This will give me x to the 4th, 4x to the 4th over 4, just x to the 4th, minus x to the 7th all over 28. And this will be bound from 0 to 2. So let's go ahead and plug in the upper bound. The lower bound is going to give us a value of 0. So we're going to have pi times 16 minus, what is that, 128 all over 28, minus 0 to the 4th minus 0 to the 7th all over 28, just going to show that I plugged in the upper bound and the lower bound. This works out real well because this lower bound goes to a value of 0. We like that. So this is going to be pi times 16 minus, so I'll go by 4, so that'll give us 32 over 7. 32 over 7, so I'm just going to use my calculator for that. And oh, I just lost something again. So hopefully I don't even know what I just lost here. I wasn't paying attention. I was on the calculator. It goes to show me. So anyway, so this portion right here will give us 80 pi's all over 7. So 80 pi's all over 7. So I think this was 128 over 7. This was minus 0 to the 4th minus 0. Yeah. So that's going to give us 80 pi over 7. So I tend to find these problems a little bit more exciting because you have to do a little bit more research to figure out what your radii in fact are. So again, using the washer method, you have to have an outer radii and an outer radius and an inner radius. The outer radius for this one was constant. I really like that. That tends to be consistent, that you're going to have a constant outer radius when you're rotating about a horizontal or vertical line that is not the x to the y axis. So it makes this problem a little bit more feasible and doable. So hopefully that made some sense for you in here. Again, washer method works very nicely because once you identify the line in which you are rotating, if it's horizontal, I recommend integrating with respect to x. If it's vertical, I recommend integrating with respect to y, and it tends to be very consistent throughout.